So then we continue with a panel. So perhaps I make the round different like last time. Perhaps I give it just a round and you just introduce again yourself, or perhaps people know you, and say why goal-orientated communication or identification or whatever is interesting for you. I start here.
Oh my God. Okay, my name is Yangling Chen. Actually did my PhD in Germany, actually on VTEP channel. So after that, I did some postdocs in Norway, in Germany, and I also had my own project. And later, this is actually the topic I was talking is actually the project before I joined the industry I was working on. And as I said, so this is totally inspired by the application. Yeah, I know this very famous identification code when I was studying my PhD, and I know it's difficult. I said I always try to avoid to read the whole paper, but I see when I was working on this topic, and I have to, and it's really a good motivation because I see it really fits the scenario, and actually did yeah did this the part I was missing. But I found I really feel a lot of fun doing this research, although I didn't impress the people from from that field that much because, as you see, that the performance probably they were more convinced with hashing. Let's say it's easy and it's well accepted. And sometimes it's very difficult to convince or to somehow convincing the people to accept a new idea and or yeah, I see the difficulty. So I was very happy, and it's really honor to be here to share this topic with you. And I also from other talks I see that. Is the progress not only on theoretical part but also on the library, and maybe this I could imagine in the near future. I hope this will become tools that this will be well accepted also by the industry, maybe also to some point standardized. And yes, I will be glad to see this happening.
Okay, thank you. My name is Usman Ali, and right now I work with ecological computing, and we're exploring like post-Shannon communications as well as other ways to save energy and reduce the data rate and how much transmission is costing. And since we are approaching this transmission capacity with the traditional Shannon-based approach, right? So yeah, I got interested into this problem because in the past I've worked with SDRs, and I had experience during my bachelor's and master thesis from TU Munich, and so work in NI. We were looking to SDRs for applications on AI, and the AI is also trying to improve the spectrum efficiency and also help like then reduce the data rate, and identification is kind of also tied in the sense of goal and semantic oriented communication by reducing transmission and saving energy, which is a major crisis in the current time. So this is my trying to bring the theory into the practical world. That's it. Thanks.
Hello, I'm Juan Cabrera. I am a postdoc at the Deutsche Telekom Chair of Communication Networks at the TU Dresden. And I got interested in goal-oriented communication during my PhD because I started to look into this problem of functional compression, which is what do you need to transmit to compute a function at a receiver? So if you have multiple transmitters and you want to compute a function, what do you have to transmit? And you can always solve this with channel communications. As long as you transmit the data, then you can compute it. But it's very interesting. The question is, can you send less in order to compute it? And what I like about this is that it felt like it generalized everything we know about information theory, because information theory was all about message transmission. And in message transmission, you can see the same problem as functional compression, but with one particular function, which is the identity function. You want to compute that entity. You want a function that returns exactly the things that you received, right? So this is message transmission. So I got very interested into this because it felt like everything we know about information theory, it's only solving this problem for one function. What if we have other functions? And then this felt like open a door. Later, Holger Bohe and Christian Deppe came to us there in Dresden, and then they showed us this concept of message identification. And it resonated with me with this area of functional compression because I thought, okay, this can also be seen as one function in particular, which is an indicator function. Is my message the one sent, transmitted or not, right? So it kind of resonated with me. And I feel now that a challenge that we have to do in this community and in this field, right, is looking beyond message identification, is try to see what other functions can we gain, when can we gain, when can't we gain, and the vision that I see or the dream that I have, right, is that if you know this is my problem, which is defined as a function, and this is my communication channel, then first, how much can I gain over Shannon by doing something? And second, how do I construct a code that do it? And if this is possible, then I think we will have found the gold nugget of the future of communication systems, I would say.
I'm Pau Colomer. I'm from Barcelona, and I actually have a broad background in physics. And then every time more theoretical and theoretical physics, I was nearly changing to mathematics at some point, but didn't in the end. Then I moved to quantum physics and I did my master's in quantum physics. And when I was applying for a PhD, I did a project with Andreas Winter about communication info. Post Shannon. Well, it's not post Shannon. So it was more like very abstract quantum information theory with entropy measures and so on. And then I got into the topic thanks to, when I started my PhD, Christian told me there was this deterministic identification results in classical. What would happen in quantum? Could you reproduce these results in quantum? And this was how I got into the topic. Suddenly, when we started looking at it, especially with Andreas, we felt that we didn't really understand why some things were happening, so we started doing more and more abstraction until we end up with what I presented today, which is very fundamental, classical, and quite abstract. And this deep relation between a communication problem and these very rooted mathematical, geometrical problems is what made me fall in love with this topic. And yeah, I guess that's it for me.
I am Alberto Perotti. I'm from Italy. I work for Huawei Sweden, and as a research engineer, my main job is to do research and provide inputs to 5G standardization, so 3GPP standardization. And my background is mainly on error correction codes and for wireless transmissions in general. I started to look into identification codes maybe less than 2 years ago, when in standardization people started to talk about very low power terminals. So for a very, very specific application case, ultra low power terminals that cannot afford, do not have enough energy to keep the main 5G transceiver on all the time. So basically the idea is to switch off the main transceiver and to keep active only a very low power receiver, which is supposed to monitor a certain subband of the signal for an incoming low wake up signal, and then wake up if the signal carries its own ID. So it's I would say, fits very well the identification coding framework, right? So we made some work. We developed a very simple scheme because we also have processing power constraints in the very low power terminal. We try to bring it to some standardization, and then the standardization process that I would say deviated a bit from identification codes. But we expect that in the future, especially we are now already seeing the start of 6G standardization in next year, probably the RAN 1, which is the group of standardization 3GPP, which is taking care of the physical layer, will already start talking about 6G. We expect that the network will grow. There will be very much larger number of terminals. And so it is expected that there will be use cases for identification coding. So we will continue to look into this and expect waiting for, I would say, more practical and flexible code constructions. That's what we need to apply them to the standard.
Okay, thank you. Then start with the question. So Marcel, I leave you out last time. So
Yeah, my question would be, so Juan already answered a little bit, but maybe one step below the theory of everything, what in your opinion is the most interesting or most relevant problem to be solved in this area of identification, either to understand the theory better, some new theoretical results that would be interesting, or to bring it into application? No, it's a question for everyone, but I would just wanted to say, okay, maybe not the theory of everything, but more feasible in the next years.
Yeah, so something that's interesting, right? It's that identification promises a lot, have these enormous gains, right? But when you look into applications, there are not so many applications that we can map to an identification problem. So this one that you mentioned of activating one node among a certain amount of nodes, one that keep reappearing, right? Keep showing up. However, we always try to find applications. So I would say from the application point of view, something that is required is a change of paradigm, right? Start thinking your problem with this tool available, right? And this is one of the papers that Caspa wrote, right? Which is, okay, let's say that you can do message identification. Then how do you make a protocol based on identification to reduce the data in order to synchronize a cyber physical system with its digital twin? And one of the challenges from the application point of view is to start thinking of the problems that you have now. How can you reformulate them in such a way that accepts identification as part of the protocol, because then you will have these gains. And then from the theoretical point of view, I would say maybe some challenge is that I see is to look more into K identification, which before the theory of everything seems like the next step. So identification and K identification, because then that will open the door to even more applications. So identification opens the door to a few, K identification will open to more, and the theory of everything will hopefully solve more.
Yeah, sorry, I was actually going to say the last bit of his speech. I think that the really interesting thing right now, like the really the big open problem that would get more people into the topic, and hopefully people even from industry or more, let's say, non so theoretical people, as I can only think in theory for some reason, to get into identification and to really think of this as a tool to solve some real problems is actually looking into K identification, and even understanding how to go from K equal 1 to a K equal the whole set, right? And seeing the how the spectrum changes from the identification or we presented today to the actual transmission problem, because the K identification with all the possible sets is obviously trivial because it will be always one, but then you would try to decode, and that is exactly the coding. So seeing the transition between identification and decoding through K identification, I think it would be a very beautiful thing theoretically.
I'm not sure if I can phrase the question clearly yet,
So we're talking about identification and k-identification. We are not so much talking, so this is kind of, we're talking about the goal that we have. We're talking about the channels and networks and so on. Okay. But what about other parameters of the models and like resources that we use? And so my example is always like if you assume something to be random or if you average over something or not. But there could be other things. So my question is to make our theory practical, basically, what other modeling issues are there actually, except what is the goal and what is the channel?
I'm not sure I'm really answering your question, but when I was working on this problem, because it's a very practical application, I actually try to model it. By considering these practical parameters. For example, I have mentioned this publicly available data set. So it's like a global data set. And also, but often what we are dealing is just a subset. So then actually this specific application where I didn't mention is that the size does matter, because we have to consider the global data set for designing the scheme, because we don't know which sample we are going to have to deal with. But actually, it's not bad for us if we are dealing with a smaller data set. Then your performance will be better because of this false identification. And actually, tricky thing is false identification. It's bad for performance. It's good for privacy. So this really that's what I mean. The statistic behavior of the subset or the data set, it's also different because it's not uniform. This actually bothered me for a while because I'm from the information theory, so I know that we try to model things and we make assumptions, and especially this uniform distribution, for example. But here we don't have uniform distribution. For example, your name. Your name, the length is also variable, and also of course, each character, probably from Germany, you have so many characters you could choose. There's the alphabet, but the frequency of the alphabet, the correlation, it's different. So this, but if you consider, it really depends also the first step. So what do you consider as an identifier? You have different attributes. Should you consider them individually or jointly? You can consider them, you can put them together jointly. And then each identifier, you will see, okay, it happened just once if you list all the populations, right? But you have a much bigger sample set. You have a much bigger, because if we define every character from the, let's say 26 or 27 field, then it depends on the length. The length is different. You have to consider the maximum length. So you have, let's say you consider like the set. For all the possibilities, actually not all the possibilities are happening. Yeah, you don't have a uniform distribution, but when the individual, when it appears in your data set, it just appears once. It's supposed to be just once. So it's very different behavior, I think. It's sometimes when I present these theoretical results, and it bothers me because I know it doesn't fit my assumption. So, but it helps again back if I look at, for example, your model, or people try to have a theoretical formulation of this identification problem. For example, from the talk yesterday or poster session yesterday, this secure identification. I see immediately it match. I mean, why I see that? Because this secret code, right? I think you have this, if it's not degraded, it's 0. If it's degraded, okay, it works fine. But this attacker scenario, imagine if the receiver or it gets access to the global data set. He doesn't have a degraded channel. He has, actually has more information. So then this actually matches this dictionary attack. So this scheme is not working against the dictionary attack, but this exactly match the information theoretical result on the VATAP channel, the identification code over VATAP channel. What do you do? What do you do? You introduce common randomness, the key. If you have a key, just known between the legitimate users, the data set A and B, and others don't know, you have everything's fine. But we studied this also in our modeling. Then you see theory, the practice, it matches actually. but it's, I'm not sure, but I really think through this communication or this occasion, I hope that maybe one of you genius could have a good reformulation of the problem, maybe from the use case, from the practice, then bring nice results. That's, I think, would be great. Yeah.
So next question.
Thank you. Yeah, this question is to whoever wants to answer it. Yeah, so coming from the DNA data storage perspective, usually we have multiple noisy reads of the same code word. And there are 2 questions you can ask in this problem setting. Either ask, okay, I have different channels with the same characteristics. Let's say every channel introduces at most T substitution errors. Then how many noisy reads would I need? Uncoded, I don't have any coding on the whatever I'm transmitting. So how many unique reads would you need in order to reconstruct the original message? Or you can ask, okay, I have only 2 or 3 distinct channels of the same behavior. Then how much redundancy would you need to pay in order to reconstruct the original code word? So can you think of if this problem is somehow applicable to identification codes, would the same result as in classical channels would also apply? Yeah, that's
Okay, perhaps I give it to Pao because we discussed it before a little bit.
Okay. I was still thinking about it. So I guess that a big problem here. So the biggest problem I would see is that so this would be applicable if you had already both encoder and decoder. Well, now let's not call it encoder and decoder, but both the person who synthesized the DNA, even if it has been nature, and the person that reads it, are aware or of a possible list of of DNA strands that can be. If not, your list is basically every possible code word in your input space, right? So once here, I mean, I don't see how you would make the connection for every possible code word in an input space to create an identification code. I think that you need to reduce this to create some encoding, which is actually reducing the set so that you get an identifier. But if you're using your whole space, I don't really see how you would do it. directly at least. So maybe on the other side, like when analyzing the data, maybe something can be done there, but directly on the strands, if you do not have the power to control at least something in the encoding, or you don't have a set of possible, so if any possible sequence is possible, and you can, you want to be able to reconstruct anyone, so any possible sequence, I don't really see how to do it. I am not promising that it's not doable. I'm just saying that I don't really see how to do it. So sorry about that. I hope someone has a better idea than mine.
Not directly to you. So if Pau doesn't have an answer, I will. Then I will never have it. No, but Dana, that you mentioned DNA, right? Something. It's also something that's been in my mind for some time. It's a pity that the professor was working on molecular left. This reminds me a little bit of the beginning of information theory, that when it became super popular, and after some time Shannon wrote the paper, hey, get off the bandwagon, information theory is not so, all these things, right? However, I think he undersold his idea a little bit with that paper. But what I want to say now is that with identification, we should look for the other approach, which is actually try to get into the bandwagon, in the sense that I think with some work that I've been doing lately with Holger Bohe, Pete, and Christian Depe, right, and also some previous work that Depe did, that there are some processes in nature that seem to be modeled better from a message identification point of view. So one of the things we're looking now is the CRISPR-Cas9 operation. How does CRISPR-Cas9 can detect and find the correct strands of DNA in an environment that is so noisy and so full of other DNA strands and so many other components and substances and molecules? How does it work so well? And it seems to be an identification process that it's doing, right? It's trying to find the correct strand out of many, and it's trying to focus, is this mine or not? Is mine or not? And there are some results that show that message identification is not susceptible to signal-to-noise ratio, which means that there are some aspects of message identification that maybe can be used to model these other natural processes, right? I know Christian has done some work on this, on the olfactory sense, right? If you smell, apparently the way your brain and your smell sense work can also be modeled as a message identification process. And I think this would be another very interesting point of view from the theory, from the theoretical aspect, right? Just like when message transmission and information theory came up, then Landau came and associated with physics and entropy, physical entropy, and then the DNA came up and everything was information. Black holes also related to information, everything was information, right? The question is there something like this that we can link to message identification or K-identification, or the next step that can be modeled in this way, and would that be helpful for something? So that's just something that I've been thinking maybe to bring to the community.
So I don't have any question, but like I learned a lot of things from this conference. So like my domain knowledge was limited, but now I have a lot of domain knowledge about this. So hopefully I will read about it, and then we have more knowledge and more questions, and then obviously I will ask from my boss about this. Yeah. Mm-hmm.
Sorry. So I was just thinking, and maybe what you could actually do using identification would be, okay, let's have 2 or 3 strands. So you say, I want to identify somehow a certain strand of DNA that has been, well, there has been some changes on some positions of this strand. There has been some error, let's say. I think that what you could really do using identification codes is, once you have watched, let's say, a couple of outputs from this single input, then identifying if another possible output comes from the same input. Does this make sense? Or I don't know if that might be useful for anything, but I think that you could really do this. So once I know, so without knowing the whole set of possible outputs that a single distribution can generate, I think that with an identification code, what you could do is, just knowing a group of possible outputs, identifying if another output comes from the same strand or not. That's okay. Sorry, that's I don't know if that might be useful for anything.
I have the feeling actually identification code, at least in my application, it's really just for exact matching. It's not very working well in a noise with a noisy thing. So it means if your DNA string, there is already some bits flipped or noise has occurred, then you want to match identification code, that work. You need kind of like a approximate matching. And this approximate matching, one I know is this Bloom filter thing. So basically you can cut your DNA string then in a way that each small part become an element of a set. Then you employ this Bloom filter, because the Bloom filter, the concept is just to test if the element is belong to the set or not. So this is actually idea of the Bloom filter was invented. And if then in this way you turn the DNA string, the noisy one, into a binary string in form of Bloom filter. If they are very close, you can consider they are the same, basically. So this is a way approximate matching. I think it's really effective. It's really a good way to go. But this is exactly what bothers me in my use case, because I also have the attributes, there noise in the names, and identification code doesn't work if you just use it once. Another way you can use it is that if you know, like you have to, as I said, it's the all approach. It's like you have to choose like most likely identifiers. Then you use the identification code, and you use the all approach. If it's one work, then you consider it work. So this is also approach to go. So it's like, yeah, but I think Bloom filter, it's really much easier to do than this one. Yeah, I actually was I consider this employing multiple ID code, but you really need to choose the identifiers carefully, and you use the approach. Or maybe there is a better approach, you try to, if your false identification rate is very low, then it works. But I think it's more complicated compared to the Bloom filter. Yeah. I don't know if it, someone smell.
I just said KID. I mean, a Bloom filter is I'm not sure if it's like if it's equivalent, but like it's more or less a K identification code.
So yeah, since yesterday I have a very stupid question, but it's important for me to understand, like, if we are talking about identification in coding, which means we have some message, we encode it to compress the data, and we send it through some channel, and we just intend to compare the message at the receiver whether it is of our interest or not. So because our tag value that we computed, we cannot actually decode that tag back to our encoded actual message. So then why we even need to secure our tag? Because no one can actually decode the our tag value to back to the original information. So why doesn't even we care about securing of the tag itself when it is of no use? We cannot decode to the actual information.
I think it depends on how strict you see security and secrecy and so on. Because in the end, if you use Reed-Solomon, for example, it is an error correction code, right? And if you know if you know the random position and the tag, you learn something about the message because you know which kind of code was used. You know the Reed-Solomon code, right? You know which kind of polynomial was used. And then you can generate a list of possible messages that would result in this result, right? And then you can brute force, essentially, right? If it's your, I don't know, if it's your private key to your Bitcoin wallet or something, and maybe someone is interested in finding it, if you generate this tag, it is possible to reverse engineer it. But it depends on lots of things, right? But it's not completely secret in that case.
The higher Kelvin field, like for example 32 or 64, we can already see that the false positive probability, or we say collision probability, is almost zero. It's like 0 point something, very last number of zeros. So I mean, even we have like list by brute forcing a lot of messages that can result in a single tag value, but still we have the false probability to be zero. So
Yes, but in that case, we look at accidental collisions. And I'm not an expert on hacking Reed-Solomon codes, but we know that there is some underlying structure to Reed-Solomon codes. And so I think it's very much conceivable that someone finds some kind of efficient attack that uses the structure of Reed-Solomon codes to invert it efficiently and to quickly find messages that differ in some places. And you, I don't know, you change the first bit and the last bit, and if you change those, then you know where the text changes or something like this, right? And then you don't have to brute force it in a stupid way, but you find an intelligent way to use the structure of the encoding to reverse engineer it. And then you don't, then it doesn't matter what is the accidental collision probability, but what is the purposeful attack collision probability. And it's a different kind of probability.
assume that the hacker has the list of all the possible messages that we are basically transmitting or receiving, right? Okay, thank you.
And sometimes you think this is unacceptable, and if you think this is unacceptable, then you need to take extra steps so the attacker can't do this, right? So either you hide the randomness, or you encrypt the tag, or you don't use a Reed-Solomon code but a random linear code, and you hide the encoding function that way because no one knows what kind of function you use. And yeah.
It depends also on the goal. Perhaps he want to know just what we assume in our example, that we have an eavesdropper who just want to know, I have a special message. Are they sending my message? Yes or no? And that's also some leakage. He don't want to know what kind of message he's asking for or what is transmitted. He just have a special message and have interest in that. And therefore we have to also, therefore we make the tag secure.
So I have a question, but the question mainly comes with respect to common randomness, and it's mainly directed to the industry people here. Um, so yeah, of course. So one use case of common randomness is in identification codes as well. But on its own, common randomness is also very useful when it comes to security part. Is there any active interest on the industry side to adopt common randomness or to standardize common randomness, for example? Because even if there is no identification, even if identification doesn't get so popular, there is still there's still the use case of common randomness as a security aspect. So do you think there's going to be future standardization or future work in the industry side just on the with respect to common randomness?
Yeah, actually, security is implemented in a very specific layer of the communication stack. I'm talking about wireless networks, wireless systems. So in principle, yes. I mean, you could use some implementation of common randomness in order to provide security at a different level, for example, at a physical layer. For the moment, in 5G networks, it's not being considered as far as I know. And also for 6G, we are already getting ready, and there seems to be, as far as I know, I mean, there are many things happening in parallel, but there is no such initiative to provide security at that layer. So for the moment, it will stay in a layer on its own. Actually, I don't know if it's answer.
I don't know, perhaps there's also this theory of denial of service attack, so where we also can use common randomness to reduce the denial of service attack or to avoid this. This might be an application. I don't know. So did you think about that?
Yeah, I mean, it's a possibility. I mean, it's something that it's a bit outside of my scope because it's on more higher layers, but it's of course yeah, possibility.
Okay, Abdallah?
Yeah, I have a question. I mean, regarding people who have started at some point in identification research or like questions related to identification, like few years later, do you think that like the feeling that there is more than that than you or what you thought initially has to be done in regarding both theory and practice, or actually you are thinking that no, it's actually like more fruitful than you initially thought regarding the potential practice, especially for example, you are in a like opening a startup or participating in some startup. So actually, what kind of product that you are thinking of right now? Is it like something like an IP, like an intellectual property that probably would be the most valuable product, or a physical product like some equipment or something, or implementation of some standard or something?
Yes, so what I've experienced, at least in industry, is that, you know, when we go from theory to practice, there's a lot of steps in between. Like from simulations, you go to some over-the-air testing through software-defined radios, and or building some kind of framework and standardization that needs to happen. Some field trials needs to happen before you could actually incorporate into, like, you know, applications and so on. But I see a lot of applications where hashes are used, right? And those applications could also be like, if we broaden the scope of identification problems, wherever like hashes are used for, you know, to avoid collisions or so on, like in messages that you want to, yeah, create, or like create unique identifiers and so on. So their ID codes could be used. And as a next step in the current state, I feel like we need to demonstrate like some examples where we can show huge gains over the theoretical, like, or the Shannon-based communication. So then we could probably, then next step would be to then like, make it part of the standards at some point. But I feel like it's still like a few years work. Yeah, continue.
Yeah, so something that we are considering is intellectual property, of course, but also we would like to provide a very highly performant library as part of our product. In the and some of the product, so the software library itself would not be the only product, but in combination with protocols. Because what we see so far, right, is that when you change the paradigm, the way you approach communication problems, and you rethink the protocol to have some to integrate identification in some step of the protocol, you can already have gains over Shannon. And then what we want to show maybe is that these gains allows you to save energy overall, because every bit that you do not transmit is a bit that you don't have to process, compute, and would not introduce this energy expenditure. So this is a way how we would eventually would like to monetize this. And another reason that we are very interested in making this highly performant library, that's why the guy has put so much effort into this, right, is because the way we see is that identification is just the first door into this new world of goal-oriented communication. It's the simplest problem that you can have. That it's a yes/no problem. And from there, then you would go, like Pau say, right, to this K identification, understand a little bit more about that. And recently from this workshop, I just learned from Johannes that he seems to be very sure that there is no better way to decode a K identification than to perform K time a single identity, which means that if this is the case, then all this effort into making a very highly performant identification library will be helpful, because then if you have to make K, then if you increase linearly, if you have this single step very slowly, then the whole thing will be super slow. But if this step is fast and performant, then K identification might open the door to many more applications, right? We would still have a solid starting point that will be performant enough to maybe implement it in some industrial applications.
I can say something. How to say, because we actually really use a lot of hash functions and AES and all these also play an important factor there is that the hardware accelerators. So it means that the hardware is specially designed and to make this calculation very fast. And there are already such microcontrollers that have this support this hash calculation, AES calculation, and even elective curve. These calculations for the cryptography, so very fast. So when really, I was positively impressed when you present this timing. So it was very efficient. So I think it's a very, it's a good point, right? So you can, in the products, I mean, performance is always the first. I mean, security, of course, you have to reach a certain security level. That's required. And then under this requirement, and you will choose the best performance algorithm. Yeah. So, but there is still also possible. For example, if you have this high performance library, and it's like last year this NIST also have standardized these post-quantum algorithms for this signature and key agreement and such as. There's no requirement to use it, but there's consideration to use this. And then if there's like a high performance library available, so it's possible to use, because I think the industry would also like to test. So or have this into consideration in the product to get a better security. And with the ID code, I see if you really have a good performance, and there are indeed also application scenarios. Maybe you can replace where the hash was used, because people use hash just because it's convenient. And I think the communication cost, it's similar as you use hash. So we can consider the ID code is basically a kind of hash. And but if you really show that the performance is great, is better than hash, even when the hash use hardware accelerators. But you could be more energy efficient and also communication efficient, because you transmit less bits and you consume less power. So this is the advantage. But at the same time, you have to show also this false identification rate is really low. So this happen almost not possible. So this is very, very important. Why people use hash, because they can be sure, okay, it's safe to use because it reach a certain security level. Under this security level, the collision risk is very, 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 very low. We don't have to consider it. But if you use ID code, I think, yeah, you have to go a bit up with this extended field, so that try to get this false identification rates really low. So I'm not sure that performance actually, but the hardware restriction could be also a problem, because currently you show that it's performant because you actually require like ARM8 or at least. But below that, many microcontrollers are actually below that, so they don't support. And the performance on those, it's not clear, I suppose, because you actually take the advantage of this architecture. Mm. Yeah.
Regarding the concerns of energy, which are like seems to be very like important for understandable reasons, why there is no that much work of identification under cost functions, or there are many, but I'm not that familiar with. I know that identification with over Gaussian channels is already like some kind of cost function. But other than the Gaussian channel, is there like a general framework for identification under cost functions? Because energy for sure can be.
I think the main thing is, of course, that it's shorter. That what I think you said that you send less bits. But of course, I agree. You can make it more general. You can introduce also a cost function and say I want to optimize via this cost function. That's something you can additionally do. I think there's at the moment. Okay, you have this power constraints and you can do something there, but that's something we have to work on, of course. But in principle, the energy taste is already there because the code words are much shorter. That's a good thing. The bad thing in the beginning was really that the decoding needs so much computing time, but that's much better now. When you remember when we start, you were also at the TUM, and Roberto did the first experiments, and we saw, okay, it's much better, but we decode forever, and we have so much to do with computing that we lost everything. And I think there we make big steps now to implement, and then we can first argue, okay, we need much less bits, and so we we save energy. But you're right, to make a more detailed analysis, one can think about some kind of cost function. I don't know, someone else want to? Okay. Is there another question? Then I will finally ask the same question like on Tuesday. I don't know, so it's very hard perhaps, and for some people I know what they would do. Again, someone came and say, I give you €1 million, so make a project of 2 years and do something for goal-oriented communication. What would you do?
A business plan. Well, I don't know. I mean, someone should really think about and make a plan. But I would say a first step that there are forecasts about how there will be evolutions in technology, right? So I mean, we have to characterize the future. For the part I'm concerned with is characterize the future networks and future applications, and so yeah, I don't know if it's something more to say at this point, but yeah.
I really have no idea. Yeah, maybe my own salary, right? I don't know. I guess that if I had that much money, I would really try to work out somehow. I mean, I'm very far from all this stuff, but the real use example that could be actually seen, even if it was a really easy control system, but just something that you could show to people and say, hey, this is much more efficient than what we're using right now because we're using identification. If we apply this to every kind of communication we have, we might have huge gains both in energy and performance and efficiency. So I guess that my aim would be, yeah, trying to work out a small example, but a practical one, such that you can show people that this really is a thing. Maybe it's the worst business idea ever, because maybe after that everyone would get into the topic, and my use case would only serve as motivation for other people. But I think that it would be interesting somehow.
Yeah, my answer is a little bit following what Pau says, and I think we need to understand how big is the pot, in the sense of how much can we really gain from this goal-oriented and post-channel communication. And that's why I emphasize this idea of going a little bit beyond identification, starting with K identification, but beyond that, the control system, right, that you can show to control this, or to control this, you need this arbitrary function. And then the question is, if you need this arbitrary function, then how much can you gain over channel? And then show as a this toy example that you can say, okay, with identification you can win this much for this particular function, but for this particular control function you can maybe win less, but you can still earn something over channel. And then we show it, because of this, then we need to push this concept of goal-oriented communication, because then we can show that there are gains in energy, maybe latency, performance, and whatnot. But yeah, I think identification opened the door to this new world of goal-oriented communication. We want to push it harder.
So we have 2 million now.
Yeah.
Yeah, this is something similar. Like in the end, any algorithm that we develop, like there's a lot of practical aspects that need to be seen, and there might be some constraints where, in theory, it might seem like possible, but when you apply it to an application, there might be some new challenges that you might discover on the way. So as early as possible, like picking one example, like there are a lot of existing problems where it's getting used, or where people are thinking of using it. So we'll spend some time on how to make like a standard way to measure like some of the challenges, like the how much energy does it consume, or how much computational power is required to be currently existing hardware, or like software supports it or not. So this is something that needs to be checked, and it might take a year or more, like to develop like this framework of generalizing this testing of different performance metrics, and then apply it to one application and pick one, and then demonstrate it to the community. Yes. Okay, thanks.
I get this question before in my work. That time, my answer is to improve the coffee machine in the workplace. People need to happy working. Then it's the best thing for productive. In the next maybe following years, but yeah. I think some of the audience agree with me. But it also shows I have no idea about the money. So I will think either I give this to some people who know where to invest, or just invest them as the people in the field. That's it.
Okay, then thank you to all of you.